Hey guys, welcome back to another video for Earth and Environmental Science with me, Mr. Forrest. Today we're going to be looking at Module 2. Now if you're in Year 11 and you've finished your first topic, this video will help give you a few ideas as to what to expect, as well as some very useful images and notes to write down. So we're focusing on plate tectonics. So when you were doing your evolution topic in Year 10, or you're looking at geology in Year 10, you would have noticed that the Earth's surface has changed considerably over the past couple of hundreds of millions of years. Now, in doing so, we had various theories as to why this occurred. Very early on, people believed that, these things just happen. That's the way that the universe was made. However, we found that evidence has shown that they have slowly changed over time. You might have heard, for instance, the fact that Australia is moving north at the same speed as your fingernails growing, which means at one point or another in the future, Australia might join with Asia. Indonesia might no longer be a series of islands, but connected to a landmass. So, when we're looking at plate tectonics, we have to look at the theory first, which states that the Earth's crust and upper mantle are combined into a single rigid layer of material we call the lithosphere. Think of it like the crust around the edge of a pizza. Okay? Now, the oceanic and continental lithospheres are named for the continents or masses that transport on top of them. So naturally, continental lithosphere is incredibly thick because it has both the underlying solid material as well as the continent on top, whereas oceanic material is thinner because it has just the lithosphere and then water over the top of it. So as such, when they collide, more often than not, you have what's called a subduction zone, whereby the oceanic crust is forced underneath the bigger one. Now, the theory of plate tectonics is nothing but the evidence that supports it. Here we have a variety of evidence, such as the jigsaw fit of the continents, which we can see with South America, Africa, India, and Antarctica, here, as well as Australia, and how the coastlines sort of match up. Naturally, they're going to be changed over time by small amounts due to erosion or deposition, but it's a pretty good fit. The location of large extinct terrestrial animals on several continents that are now separated by oceans. So if I'm looking at, say, the Lystrosaurus, this one here, it has evidence found in Africa, India, and Antarctica. But seeing as those are hundreds of kilometers apart today, we can put forward the idea that it supports plate tectonics, as this animal once lived on all three of them when it was one landmass rather than several. Geological boundaries that match across continental borders. So it might be that it has similar rock formations or similar deposited material. The shape and age of the seafloor, the absolute age dating of hotspot volcanoes, we use absolute dating, and the age dating of seafloor, basalt, and sediment drill core samples. Now, we will cover this, but this is just a list of the evidence that we tend to use. Now, tectonic movement for a long time was one of the underlying reasons why the theory of plate tectonics didn't really take off. I mean, we could explain why these continents could be connected at one point, but the underlying drive of why they moved apart was still missing. So when Wegener, for instance, put forward his continental drift theory, he was missing the locomotion that caused the continents to move, and as such he wasn't immediately believed. Holmes, however, provided the idea that the convection currents in the mantle were causing the top of it to slide, or what we have called slab pull. So in 1912, we're going to propose the continental drift hypothesis, which was the forerunner to current plate tectonic ideas. Originally, Alfred Wegener and Alfred Russel Wallace and Charles Darwin all had different ideas, or similar concepts about why different continents would have similar organisms. And they all believed that at some point maybe the land masses were connected and these organisms had similar ancestors. As they separated, they became isolated and evolved towards different conditions. Much like how if you and your friends went to a party, but when you got there after about an hour, you all decided to go off and do different things. If you were to check your photo reel the next morning, your photos at the start of the night would be very similar. But as the night progressed and became more and more isolated from each other, the photos would become more and more different. Now, Harry Hess, around about 48 years later, in 1960, proposed seafloor spreading model, which is as the plates move apart, the magma that came up through the center would cool, form basalt-based material, and as the plate moved apart, it would crack and release more magma, and so on and so forth. Whereas if it was forced underneath another plate, some material would be forced underneath, it would melt again, and then join back into the convection current. The deep sea drilling program collected seafloor sediment and basalt samples that confirmed that the seafloor is progressively older the more distant it is from the mid-ocean ridges. So if you look in this picture here, the ridge is where the seafloor actually is made. Now as we're moving to either the left or the right, we notice that it gets older and older, the oldest portion being just on either side here where it reaches the trench. Once it's pushed underneath another continental plate, it goes back here into the mantle where it's superheated and melted down again, much like a conveyor belt. Now the theory of plate tectonics, while it explains a lot, it's not complete yet. There's still some room to answer a few questions. Maybe one of you could do it. Now the theory of plate tectonics was developed by approximately 30 to 40 people during this time period. Their breakthroughs are as follows: a detailed mapping of the seafloor shape, understanding of seafloor magnetic stripping, age dating of seafloor based on magnetic stripe studies, more convincing reconstructions that demonstrate jigsaw fit of the continents based on more detailed maps of the continental edges, discovery of terrestrial plant and animal fossils such as the Lystrosaurus fossils in Antarctica, and earthquake distribution studies that identify the plate boundaries. Now, if you need to, pause the video and go back and make sure you have some of this information written down, because having an idea is only a small part of science. Most of the evidence that supports it is crucial. Now, plate boundary types are also important. Here is a map that conveys the different types of boundaries along with where they're located. So Australia is located here on the Indo-Australian plate. Now each of these different edges represent which direction it's moving. The light blue indicates that it's moving away from each other. So here we're moving away from the Antarctic plate. We're moving north, it might be moving south. Convergent plate boundary is where they're crashing into each other. So the Indo-Australian plate is moving towards the Eurasian plate, the Philippine plate, and the Pacific plate. The purple indicates a transform boundary. So instead of moving away or towards, the transform boundary means moving side by side. Now you can see here that some of these island areas, for instance New Zealand, are where we have large amounts of earthquake activity. If you take both of your hands like this and you interlock your knuckles, if you try to move one fist up and the other one down, your fist has to jump over the knuckle. This friction and the resulting sound is similar to the forces that create an earthquake, but it's not the only type of earthquake available. So having a picture like this is really helpful, particularly when you're trying to identify divergent, convergent, and transform boundaries, because if you can do that, you can predict the type of behavior involved. I apologize for the noise. So here we have divergent plate boundaries. So a constructive plate figure, and here we have what we call a hanging wall. So divergent plate boundaries form when heat from the center of the Earth causes magma to form solid convection cells. Hot magma rises and lifts the lithosphere flowing sideways underneath it. The lateral flow drags the plate in the same direction. So if you create a convection current and you put some foam pieces on top of it, the foam piece will move in the exact same direction as the convection current. Now, typically basalt is the first material to form because it's an igneous stone and it forms when the magma is rapidly cooled. So if we have a divergent plate boundary, we can assume we're going to find tons of basalt there, where we have assistance in pushing plates away from one another. Rift valleys are low regions of plate caused by a movement of underlying mantle material, often collecting water to form linear lakes and major rivers. They're found in both sides of normal faults. A normal fault is equals the vertical section of the lithosphere drops down relative to the area on another plate. So like here, this is a normal fault. Both Rift Valley and mid-ocean ridges can be deformed by transform faults. So the geological features that we can find in a transform boundary can be distorted over time if they're exposed to a transform fault as well. You're not always going to be moving away from each other or towards or side by side in clear-cut directions. Sometimes it can be both or several. Now a convergent plate boundary is the exact opposite. Instead of the two plates moving away from each other, they go towards. They can include oceanic to oceanic, oceanic to continental, and continental to continental. So oceanic to oceanic, oceanic continental, continental continental. Older oceanic lithosphere becomes thicker over time due to what we call underplating. So if an oceanic lithosphere plate has been there for hundreds of millions of years and hasn't been disturbed yet, then odds are you can have cooling material forming another plate underneath it, so it's adding to the thickness level. Now, as subduction occurs, an accretionary wedge, which is a collection of minerals scraped up of the subduction plate, can form, while volcanoes also form as an oceanic plate subducts under a continental plate. So if we're looking in this area here, collection of materials scraped up off of subducting plates. So this trench area where the oceanic plate is being pushed under might be where we have an accretionary wedge forming. Imagine it like crumbs almost, where this area is being devoured underneath. So it's being scraped off like barnacles. Now the volcanoes form as the material goes underneath because we have an excess material and we're also going to have a very high level of activity. When a subducting plate from an oceanic crust goes underneath the continental, it's not just sucking in earthen material, it's also going to take in seawater as well. Now when that seawater has been superheated, it changes into a gas and creates huge amounts of pressure. So the volcanoes that are in this area are known for having what we call pyroclastic bombardments, which is the classic volcano shooting molten rock out of the top of it. The molten rock needs propulsion. That propulsion is the boiled seawater that is released as gases. The oceanic lithosphere can be tracked as being subducted by earthquakes generated by friction between the subducting and overriding plates. So when one plate's going underneath another, it can create friction. That friction creates snags, and then the sudden release of energy can result in a shock wave we call an earthquake. Island chains are an arc shape. In an arc shape are an indicator of oceanic to oceanic plate collisions. So if we have two oceanic plates colliding with each other, there are going to be huge amounts of heat and pressure. It can result in volcanic eruptions, which forms small islands. For instance, Japan, perfect example, or New Zealand. When two continental plates collide, subduction ceases and folding and faulting occurs, instead forming mountain ranges due to similar thickness and mass. Perfect example is the Himalayan mountains located in Southeast Asia. Okay, we have the let's go back and have a look. So we have the Indo-Australian plate over here, and it's colliding with the Eurasian plate. Now both of them are not going to say, you know what, I'll go under. Instead they both go up, resulting in a huge mountain range forming in northern India. Japan, most of here we have Indonesia, Thailand, etc. We have the Polynesian Islands, we have New Zealand, all of them are oceanic to oceanic. As a result, a lot of those islands are known for having large amounts of volcanic activity. Now here we can have a transform plate boundary. Now transform plate boundary is resulting in two plates moving side by side, and they often have a huge amount of energy being resulted. Now let's say, I'll just blow this up a bit. Let's say we want to look at the structure of an earthquake in particular. Now, what I'm going to do is we're going to have two plates. Each one's moving in a different direction. So one's moving forwards, the other one's moving backwards. Now the X represents the points of the earthquake origin, what we call the earthquake's foci. Now, depending upon the friction and structure of that fault line, it could be several hundred meters deep, it could even be several kilometers deep. But the point is that once that snag is released, it releases that kinetic energy in subsequent waves in a unilateral direction. Now, we will be covering being able to measure earthquakes later on, but I thought it'd be an important point, particularly with transform boundaries. So, there's not a lot for today's lesson, so please ensure that you have a crack at some of these questions. If you finish the topic and you're unsure as to what I meant by any resource covered in this video, then please talk to your EES teacher as soon as possible. As always, I've been Furry. You guys have been amazing. I'll see you around.